Hey folks, today's topic is implicit differentiation. So I'll talk a little bit about what we mean by the word implicit if you don't know the definition of that word. But I want to start off talking about this notation that we really haven't used a lot of. All right, so this notation means, we did talk about it, this is the verb to take the derivative of this. So this means derive whatever's in the parentheses according to x. Now, since we don't know what the derivative of y is, the best we can say is that this is the derivative of y according to x. Where this is a verb, this means to take the derivative of this. This is the noun, this is the derivative of y. Okay, well, let me show you with an example what I'm talking about here. Let's try to take something like d dx of, let's say, 2y cubed. Okay, so that means take the derivative of this according to x. Well, I can derive this according to y, and then I still have to derive the y part, though, according to x. I'm not explaining that very well. All right, so let's take the derivative. If this was an x, so I would derive 2y to the third. That would be 6y to the second times, now this is a chain rule scenario. It doesn't feel like it, but this is a chain rule because we don't know what y is. Now, we think of y as just being a number, but y could be anything. And since we're deriving y according to x, we don't know what the derivative is of y according to x. So the best we can do is just write dy dx. Okay, so why haven't we done this before? Why doesn't this matter when it comes to x's? It's because we're deriving according to x. D dx of 2x cubed. Okay, so x is our something. Something cubed. The derivative of 2 something cubed would be 6 something squared times the derivative of that something according to x. Well, wait a minute. Now, in this case, I've got dx over dx, and what's anything divided by itself? This is equivalent to 1, so I would just get 6x squared. That's why we didn't show you this before, because it really wasn't useful before. It would just be more confusing to have us write dy dx. Dy dx, though, we know is equivalent to, I want to show that this is equal to, dy dx is equal to 1. So I would do 6x squared times 1, which would then be 6x squared. Now look, if I go up here, though, I derive y according to x. That doesn't cancel. But what if I change this? What if I change this to d dy of 2y cubed? Okay, now this is a different, look at this noun, or sorry, this verb. This is saying take the derivative. This means take the derivative of this stuff according to the variable y. So now when I derive this, this is 2 something cubed, which would be 6 something squared, times the derivative of that something according to y. Now this time the dy dy cancels out, and I get 6y squared. So who you're deriving according to makes a big difference. Actually, this class was, I took this, it's called partial differentiation. I took that class, was my last class at Michigan State in the math department, and I needed a 4.0 in it to get to average a 3.0 grade point average in the math department, and I got it. I got a 4.0. It was pretty tough, but it was also like my it was my last year at Michigan State, and it was the first time that I went to office hours, that I ever went to go see a professor, which was so stupid now looking back on it, but whatever. Okay, so let's say that I try to derive now d dy of 2x cubed. All right, now the game has changed. My verb is take the derivative of 2x cubed of 2 something cubed according to y. So when I derive 2 something cubed, that's 6 something squared times, but now I need to derive the x according to the y, and then this would be my answer. So do you see the difference? Do you see who you're deriving according to makes a big difference? Okay, so hopefully that made some sense on why we're going to be writing this dy dx, or we're going to actually write a lot of y primes in there, and I'll show you what I'm talking about. But we need to do this. Why didn't we have to do this before? Because all of our functions before had y by itself. That's this phrase here called an explicit form. Explicit means obvious. It's obvious who this equation is solved for. It's solved for y. That's explicit. Implicit means like subtle, not obvious. We don't know if this is an equation for x or this is an equation for y. It could be either equation. So up to this point, all of our forms have been explicit, which is very easy. We derive according to x. We would get y prime equals blah, blah, blah. Explicit, when I derive according to x, I run into a problem because the x and y are mixed together. Okay, so what we're going to do in our first two examples is show you the difference between how to solve. Sorry, let me try again. To find the derivative of an explicit scenario. First of all, do you guys notice these are the same? If I multiply by x, I get xy equals 2. If I divide this one by x on both sides, I get y equals 2 over x. These are the same equations from a different perspective. And what we're going to do in these two examples is we're going to show you that when you derive this, you're going to get the same result. Okay, so find the derivative dy dx of y equals 2 over x. That's explicitly solved by taking the derivative of both sides according to x. Now, when they say take the derivative both sides according to x, it's kind of annoying, but you have to write out what you're doing to both sides. I'm taking the derivative according to x of y. I'm taking the derivative according to x of, and I'm just going to do a quick rewrite on this. I would rewrite this as 2x to the negative 1. Okay, so we would derive this now. d dx of y, the derivative of y is dy dx. We can't really do much more with that. Over here, we've got some stuff that we can do. So I would do 2 something to the negative 1 would be negative 2 something to the negative 2 times the derivative of that something according to x. Now, again, this is nice because this cancels out. And so we're left with the result of dy dx equals negative 2x to the negative 2, which then I like to flip it back into the format that it was given to us. So I like to put that back on the bottom. I would get negative 2 over x squared. All right, now let's try to replicate that process, but this time we're going to derive this according to an implicit scenario. So I'm trying to find the derivative of this, but the problem is I'm not solved for y. So we're going to do the same thing. We're going to take the derivative of both sides. So I would take d dx of xy equals d dx of 2. All right, so let's try to derive this. First of all, you've got to remember your rules. All of your rules still apply. All the stuff we did back in Unit 2 is all still out there. Or sorry, earlier, this is Unit 2. Earlier in this unit, chain rule, product rule, quotient rule, trig derivatives, sum rule, difference rule, all those still apply. So I'm trying to take the derivative of two things multiplied together. So this is a product rule. So if I'm going to do a product rule, I'm going to use my u's and v's, or we might be to the spot by now where we don't have to show our u's and v's anymore. That you can start to do this from memory. Okay, so let's go. This is my u, this is my v. So u prime v. U prime would be 1 times v, which would be y, plus u, which is x, times the derivative of y. Now here we go. What's the derivative of y according to x? The derivative of y according to x is dy dx. Now let's say that you didn't do it this way, or then derive 2, that's a constant. I don't care what I'm deriving according to. If that's my constant, its derivative is always 0. Now let's say I went too fast there. I'm not going to do u's and v's very often anymore because I can do it in my head. But I'll just go through and I'll show my work over here again. U equals x, u prime equals 1. V equals y, v prime equals, what's the derivative of y? Y prime. But that's the same as this notation dy dx. By the way, if you want to write y prime instead of dy dx, that's fine. That's fine. You don't have to write dy dx every time. All right, so now we're here. We want to go again trying to solve for dy dx. So what I'm going to do is I'm going to subtract the y to the other side. So I would get x times dy dx equals negative y. Then I would divide both sides by x. So I would get dy dx equals negative y over x. Okay, now this looks very different. This looks very different than what we have up above. But it's actually the same thing, believe it or not. So these are the same thing. So what I'm going to do here is remind you that y is the same as, remember, y is equal to 2 over x. Remember that? I mean, that's what you got when you solved for y by itself. So what I'm going to do is I'm going to put that 2 over x in here. So let's see what this equation now looks like. Dy dx equals, now, instead of being y, I'm going to put 2 over x in there. So that's a negative. I'm taking out y and I'm subbing in 2 over x over x, which we know the only way to handle this is a fraction divided by something is to do a flip and multiply. So I'm going to do a flip and multiply. I get 1 over x up there. If I multiply straight across, I get dy dx equals negative 2 over x squared. I hope that looks familiar because that's the same as what we got up here. Now, by the way, you don't have to do that. You're allowed to leave your answers like this. You don't have to go through that extra work. This is extra cleanup. Which is not always needed. And to be honest, it's rarely needed. But if you need it, but sometimes, maybe they'll do a multiple choice where you have to do some cleanups. So here's the point. If you derive explicitly or you derive implicitly, you have something that's equivalent to each other. They might not always look the same, like these two don't look the same, but they actually are the same thing because we remember that y is a relationship between x. So a couple of things to point out here. When you derive y, you get this new thing called y prime at the end. So every time you derive y according to x, you got to put a little y prime at the end of it. The other thing I want to point out is I'm not going to show I'm not going to show this anymore. Not usually needed anymore. I'm not usually going to do this anymore because I can do most of this in my head. All right. Now, if you need it, do it. Get it. I get it, man. When I was first doing this, yeah, I needed to show my work on that because I couldn't do it in my head. But I'm making a prediction that eventually you'll get to a spot where you don't have to show all your work on it. Okay, so notice that which way is way quicker? Obviously, this way is way quicker. So if you can get an equation that's not solved for a variable, solve it for that variable if you can. If you can't, then you're stuck with implicit differentiation. All right, so that's kind of what the back part's talking about here. Excuse me. All right, so in the first two examples, we had the option of differentiating explicitly or implicitly, but most of the time we will use implicit differentiation when you're looking at a function that's not a function of a single variable. Most of the time, it makes it impossible to get x or y by itself. So the first note is just because an equation isn't explicitly solved doesn't mean that it can't. Your first step, never not always, one of those things, never not first. Your first step is to analyze whether or not you can solve for one of the variables. And it doesn't matter which one. It really doesn't. But your goal is to get y by itself if you can. Then the next step, if you can't get one of the variables by itself, then you're going to take the derivative of both sides. Now, you must show this. You must show that you're taking the derivative of both sides with respect to x. That's this. So I need to write that dy dx thing. It does get annoying. I just did the answer key again. I redid my answer key for this unit, and yeah, it does get annoying. But if you're doing an implicit derivative, make sure that you're writing dy dx on both sides. And then it doesn't matter. It matters not if you use dy dx or y prime. If you're going to be a y prime person, you better be somebody who writes pretty neat, because you don't want to get y prime mixed up with y to the first. Now, for me, that's never going to be an issue because I never write y to the first. I just write y. So that usually isn't a mix-up. ddx is nice because it stands out more prominently, but y prime is faster. I'm almost always a y prime person. I very rarely write dy dx. But if you wanted to, you could. Dy dx is the same as, I'm using a lot of yellow highlighter in here. I don't like that, but dy dx or y prime are fine, whichever one you want to use. All right, let's get after it. Okay, so put for the equation, y equals blah, 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 find dy dx. Life is good here. Life is good because we've got y by itself. So we can just derive this thing. Now I'm going to try to get in the habit of writing the dy dx stuff around it. So ddx, I said dy dx, I meant just dx stuff. ddx of y equals ddx of x plus secant of y. Ooh, we get a trig derivative in here. All right, pretty straightforward. All right, the derivative of y is y prime. Like I said, you could write y prime or dy dx. This is a sum rule. I don't usually write out sum rules because I can just do it in my head. So what's the derivative of x is 1 plus, okay, what's the derivative of secant of y? Well, let's go back and think, what's the derivative of secant of x? You have 5 seconds. 4, 3, 2, 1, 0. The derivative of secant of x is secant x tangent x. So what's the derivative of secant of something? Secant something tangent something. So what's the derivative of secant of y? Secant of y tangent of y. Now, because we are deriving this according to x, that means that and this is a y variable, that means that we need to attach another y prime because that's our something. The y is our something, and when we derive the y, we would get y prime. We don't know what the derivative exactly is, but we know that it exists. Okay, so now we want to get this, we want to find dy dx, which means we want to get y prime by itself. The way we do this, it's pretty simple. You get all the y prime stuff to one side, you get all the non-y prime stuff to the other side. So what I'm going to do here is I'm going to take this and I'm going to subtract it over here. So I now have y prime subtract secant of y tangent of y times y prime equals, and then there'd only be a 1 left on the other side. Now the reason we do this, the reason we move all the y prime stuff to the same side is because that guarantees that everything has a y prime. So this has a y prime and this chunk has a y prime, which means I can factor that y prime out front. So I can take out a y prime. Now when I divide y prime by y prime, be careful, it's 1, not 0. And I divide out the y prime, I still have the secant of y and the tangent of y. And now we get y prime by himself. And this will always be connected by multiply, so what we can do is we can just divide this to the bottom, and we get 1 over 1 minus secant of y, tangent of y. Now wait a minute, they asked for dy dx and we wrote y prime. That's okay. Dy dx and y prime are the exact same thing. If you wanted to, you could take out y prime and you could put in dy dx. Okay, in example 3, we were asked to find the variable of the variable equation for dy dx. Sometimes we're only interested in figure out the slope. That does happen quite a bit. So there's a couple of different ways that we can handle that. Like for instance, let's look at this next one. So find the slope of this graph. This is some crazy graph. It's probably like an ellipse or I don't know. I shouldn't even say that. We could get out our Desmos and graph it, but I'm not even sure what this would make. But what we want to do, it's going to make some curve. And what we want to do is we want to figure out the slope of the curve, the tangent line at, not the tangent line, but the slope of the tangent line at the point 1 comma negative 3. So what we're going to do is we're going to do just like we did up here. And then at the end, we're going to plug in these two x and y numbers in for x and y in the derivative, and that should find us the slope. All right, so first of all, we have to find the slope. That means I need to take the derivative. If you're going to take the derivative, you want to take the derivative according to x of both sides. So I need to write that out. d dx of y cubed plus y squared minus 5y minus x squared equals d dx of negative 4. Now I'm going to derive all of this according to x. That means when I derive the y piece, I've got to make sure I put a y prime or a dy dx at the end of it. So the derivative of something cubed is 3 something squared, but that's a y, so I have to still do y prime. Plus the derivative of y squared is 2y, but that's a y, so I have to do y prime. Okay, be careful here. What's the derivative of negative 5x? It'd be just negative 5. So what's the derivative of negative 5y? It would just be negative 5 times your y prime. Now, this is an x term, which means when I derive according to x, I don't have to write anything fancy afterwards. I would just get 2x and then times dx over dx, which would always be 1. Equals, what's the derivative of a constant? I love to derive constants. Very simple. Okay, my goal here is to get everything with a y prime on one side and everything else to the other side. So this one's pretty easy. So I'm going to bump this to the other side. So I would get 3y squared times y prime plus 2y times y prime minus 5 times y prime equals 2x. All right, if you'll notice, every single term has a y prime, which means I can factor out that y prime and get 3y squared plus 2y minus 5 equals 2x. Remember, our goal is to get y prime by himself. That means I need to now get rid of all this stuff that's connected by mult. So I'm going to divide it to the other side, and I get y prime equals 2x over 3y squared plus 2y minus 5. Okay, life is good. Now that's helpful. That's an important piece of information because we're trying to find the slope by finding dy dx first. So let's actually box that in. They wanted us to find dy dx. Now I wrote y prime instead of dy dx. That's fine. But then we're supposed to now use this to figure out what the slope is. So what I can do is I can take this and I can plug in values for x and y and figure out what that slope would end up being. Let's go with red. All right, so I'm now going to take this. Actually, I'm going to go with orange. Red's fine, red's fine. So now I want to take this derivative and I want to figure out what's happening at these two values. This is my x and this is my y. So y prime at 1, -3. So then I'm going to take y prime is equal to, plug in 1, so that would be 2 times 1 over 3 times -3 squared plus 2 times -3 minus 5. All right, let's see if we can figure this out. 2 times 1, that part's easy. This is where it's going to be a pain. So that's 9 times 3 is 27, minus 6 minus 5 ends up being 2 over, that's 11, so 16. 2 over 16 ends up being 1/8. Now, what's cool, if this was a free response, you could have stopped right here. Actually, you could have stopped right here. Anyway, okay, so what is the slope of the graph at 1, -3? This tangent line has a slope of 1/8 at x equals 1 and y equals -3. All right, now we're going to go through this process again. It's going to feel a little repetitive here, but we're going to do it again to show you it's always about saving a little bit of time. It's always about trying to find tricks and ways to make this an easier process for us. So let's do this again. So we already know what the derivative is from before. Let's go. We'll do the whole thing. All right. So we're going to derive this again. So I'm going to take the derivative of y cubed plus y squared minus 5y minus x squared equals equals d dx of -4. Let's have you practice that. Pause it if you haven't. I know we just did it, but try it again on your own. I kind of went quick on the last part. Try it on your own. Okay, let's see. If you didn't pause yet, pause. Let's see how you did. So this would be 3y squared, y prime, plus 2y times y prime, minus 5 times y prime, minus 2x equals 0. Okay, so last time what we did was then we did algebra from here to try to get y prime by himself. Oops, I forgot a little prime there. What we did before now is we factored out a y prime, we moved stuff over, factored out a y prime, solve for y prime. The other option is that you can plug in your x and your y before solving for dy dx. So now I can take this x and this y and I can plug them in before and then move stuff around from there. So let me show you what I'm talking about. So this would be 3. I'm going to take out the y and I'm going to replace it with -3 squared times y prime plus 2 times -3 times y prime minus 5 times y prime minus 2 times 1 equals 0. So what I'm going to do here is I notice that everything already has a y prime, so I'm going to do two moves at once. I'm going to take out all this y prime stuff, and I'm going to move this to the other side all in the same move. I hope that's not too much for you, but we'll see how it goes. So I'm going to take out a y prime. That's going to leave behind 27 minus 6 minus 5. I hope that looks familiar. And then I'm going to take this negative 2 and I'm going to bump it to the other side. And what do you notice? We're in the same boat that we were last time. So I would get y prime equals 2 over, that was 16, which equals 1/8. Okay, so there's an argument to be made from either perspective. Maybe you thought this was faster to take the whole derivative and get y prime by itself and then plug in, or is it faster to plug it in sooner and then just go get what you need? I don't care. You can decide. You get to decide that on your own. Okay, so yeah. So if you'll notice in this next part, they're saying, notice in example 4 and example 5, they gave us the full point. They gave us the x value and the y value. A lot of the time, most of the time, they only give you an x value. So that means you have to go find your y value. So usually they only give you an x value. That means you got to go get your y value. All right, so let's go ahead. It says find dy dx at 1. At x equals 1 for this equation. So this is the same as what we did up above. This is the same idea. I'm trying to figure out what's the slope of this curve let me try again. What's the slope of the tangent line of this curve when x equals 1? So I need to first figure out the slope. So I need to figure out what's the derivative of this. So I would take d dx of y squared plus x equals d dx of 2xy. All right, now I'm looking at how to derive these. I notice that this one has a product rule. This is a sum. I usually don't write sum, but whatever. And then this one is a product. I'm going to try to encourage you to do the product rule. See if you can do it without using the U's and V's. If you need the U's and V's, go for it. Doesn't hurt you to do it, but see if you can do it without it. All right, so pause it here if you haven't. All right, let's see how you did. So this is a sum rule, which means I just derive each piece. The derivative of y squared is 2y, but I need a y prime. The derivative of x is 1. Okay, product rule. So my u, always attach the constant to your u. So my u is 2x, and my v is y. So what's the derivative of 2x? Maybe it'd be helpful if I wrote that underneath here. U times v. So my u is 2x. U prime would be 2 times v plus u, which is 2x, times y prime. There we go. Now look, like I said, if you can't do that, go over here, do your u's and v's. Now I want to get this, I need to figure out what y prime is, which means I need to reorganize things so that y prime is by himself. So I'm going to do a double move here. I'm going to take this chunk, I'm going to move it over here, and I'm going to take that 1, I'm going to move it over there. So I now have 2y, y prime, minus 2x, y prime, equals 2y minus 1. Now here's another thing that saves you a little bit of time. Once you have the y prime here, you can just factor it out in your head and then just know that this, whatever's left over, is going to get divided to the other side. So what I mean by that is I know that it's going to be y prime. I have 2y minus 1 over here over, and then what's attached here is 2y minus 2x, which I know I'm going to have to divide it anyway, so it saves me a little bit of a step. All right, so it says find dy dx at x equals 1. So this, I don't want to box this in. This isn't my answer yet. This is just half the battle. Okay, so it says figure out what's happening when x equals 1. Well, that's all fine and dandy here, but unfortunately, I need a y value as well, and they didn't give me a y value. That means that I have to go get my y value. So find y. And the way I find y, if x equals 1, is I take my point machine. Remember how we talked about this? The function is the point machine. The derivative is the slope machine. I'm going to take my point machine and I'm going to sub in 1 for all of my x values. So I would have y squared plus 1 equals 2 times 1 times y. Clean this up a little bit. Y squared plus 1 equals 2 times 1 is 2 times y. All right, my math voice. This goes back to my algebra 1 technically, but definitely our pre-calculus. If you've got a y and a y squared, the only way to solve this is by, hopefully you said factoring. And before I factor, I've got to get things equal to 0. Then I factor this. This is what? Y minus 1 equals 0. Therefore, y equals 1. Therefore, our point is the point 1 comma 1. That's kind of boring, but I guess we'll have to live with it. All right, so now we're going to figure out what's the slope. Now we want to find, let's go with a nice blue here. Now we want to find dy dx at 1 comma 1. So that means I'm going to take my equation from here and I'm going to plug in 1, 1 in it. So y prime equals 2 times 1 minus 1 over 2 times 1 minus 2 times 1, which equals, so that's 2 minus 1 is 1 over, alarm bells going off, ding, 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 ding. Notice, this is that scenario that we worked on way back in unit, actually we did it first in unit P, the first unit. We've got something that doesn't equal 0 on the top and does equal 0 on the bottom. What does that imply? That implies a VA. And if you have a VA, then this means we have a vertical tangent line. This means that we have a vertical tangent line. If you have a VA, that creates a vertical asymptote type thing, which means our tangent line there would be vertical. So our slope is infinity, essentially. So a vertical tangent line, vertical, let me leave a little note here. Vertical means equation x equals h. All vertical lines have the equation x equals 8. So find dy dx at, I guess we didn't need to find the actual equation. We just needed to find the slope. We'd say that we'd say dy dx doesn't exist. Dy dx equals dne. So y prime equals dne, or infinity. But more likely what they would ask there is, what's the equation for the tangent line? So if they said, what's the equation for the tangent line? Let me get a different color here. Let's add that at the bottom. Equation of tangent line would be x equals 1. That's our x value. They didn't ask for that, but that's pretty likely what they would normally ask for. All right, so this kind of brings back a couple of things from the past. So let's highlight these in this box here. So when your derivative is a quotient of two variable expressions. So in other words, when you take the derivative and you get something over something else. Remember, A horizontal tangent line occurs when you have a 0 over the top and not a 0 on the bottom, because that equals 0, and so that means your graph levels off at 0. We have a vertical tangent line when you get a 0 on the bottom and not a 0 on the top. And then you don't get a tangent line. No tangent line exists if you get 0 over 0. That makes sense. Okay, so I'm going to put this, let's actually write that after each one of these. I'll do it in blue, I guess. This is 0, which means it exists. It has a slope of 0. The number 0 exists, right? You could have a line with a slope of 0. It goes horizontal. You have a vertical tangent line. This is a VA. This is a slope that's undefined. And then this means that your slope has a hole, which means there is no slope at that spot. Okay, well, I'm going to stop there. And I'd encourage you to start to attack some of your homework so that you're not overwhelmed after the next video. Good luck.